Welcome, curious minds, to the deep dive. We often think of water as just water, simple H2O, the universal solvent. But what if it's more like a complex chemical stage, a place where there's this constant, delicate balancing act going on?
That's a great way to put it. It's absolutely a dynamic stage. These aqueous equilibria, these balances in water, they're constantly shifting, striving for stability.
And those shifts, even subtle ones, can have huge consequences, right? For life, for industry.
Oh, definitely. From our own bloodstream to the health of the oceans, understanding this chemistry is, well, it's fundamental.
So today we're diving into exactly that. We're taking a chapter called Additional Aspects of Aqueous Equilibria from a really solid chemistry textbook, Chemistry, the Central Science, and we're going to, unpack it.
Our goal is to make these sometimes dense concepts clear, show you why they matter in the real world, and maybe reveal some surprising chemistry you hadn't thought about.
Exactly. Let's get started with something called the common ion effect. We know about weak acids and bases ionizing a bit in water, but what happens if an ion they produce is already floating around in the solution?
The common ion effect. It's a fantastic illustration of Le Chatelier's principle. Basically, if you add an ion that's common to an existing equilibrium, meaning it's already a product of that equilibrium, the system pushes back.
Pushes back. How so?
Well, Le Chatelier's principle says if you disturb an equilibrium, the system shifts to counteract that disturbance. So if you add more product, the equilibrium shifts back towards the reactants to use up some of that added product.
Okay, give me an example. Let's say we have acetic acid, vinegar acid. It sets up an equilibrium, releasing some H plus ions and acetate ions.
Right. Now, what if you add sodium acetate to that solution? Sodium acetate is a salt. It dissolves completely, flooding the solution with acetate ions.
So acetate is the common ion here. It's common to both the acetic acid equilibrium and the added salt.
Precisely. And because you suddenly increase the concentration of acetate ions, the acetic acid equilibrium shifts to the left. It consumes acetate ions and H plus ions to reform acetic acid molecules.
So the result is less H plus C, meaning the solution becomes less acidic.
Exactly. The ionization of the weak acid is suppressed. It's a really powerful way to control the pH of a solution.
That's actually kind of cool, like tuning the acidity. And I assume the same logic applies if you have, say, a weak base like ammonia and add ammonium chloride.
Absolutely. Adding the ammonium ion pushes the ammonia equilibrium back towards the reactants, decreasing the hydroxide concentration and lowering the pH. It makes the solution less basic.
So this isn't just a theoretical curiosity. It has real practical uses for controlling how solutions behave.
It really does. And it leads us straight into one of the most important applications of this principle, buffers.
Buffers, yes, you hear that term a lot. What exactly defines a buffered solution?
Well, simply put, a buffer is a solution that contains significant concentrations of both a weak acid and its conjugate base, or a weak base and its conjugate acid.
And their main job is to resist pH changes.
Yeah, that's the key. They can absorb small additions of strong acid or strong base without letting the pH swing wildly. They act like a pH shock absorber.
And the applications are huge. Let's talk biology first, our blood.
Our blood is a prime example. It's buffered primarily by the carbonic acid bicarbonate system. This system works tirelessly to keep our blood pH incredibly stable, right around 7.35 to 7.45.
Which is a super narrow range. What happens if it goes outside that?
Bad things. Even small deviations lead to acidosis if it's too low, or alkalosis if it's too high. Both can be very dangerous, even life-threatening. Our bodies are exquisitely sensitive to pH.
And we have ways to help that buffer system work, don't we? Like breathing.
Yeah, it's amazing. Our lungs control CO2 levels. CO2 reacts with water to form carbonic acid. So by adjusting how fast we breathe, we can tweak the carbonic acid concentration, which directly affects the buffer equilibrium.
Wow. And the kidneys played a role too.
Kidneys can remove excess bicarbonate ions or retain them as needed. It's this constant coordinated effort between the buffer itself, the lungs, and the kidneys to maintain that crucial pH balance.
And that balance affects other things too, like oxygen transport.
Critically, hemoglobin's ability to grab onto oxygen is pH dependent. When tissues are working hard and producing acid, the slight drop in pH actually helps hemoglobin release oxygen right where it's needed most. It's all interconnected.
Incredible, just built-in regulation. And outside the body, where else are buffers essential?
Oh, all over industry. Chemical processes, pharmaceutical production, dyeing textiles, fermentation. Anywhere precise pH control is needed. Think microbiology labs, growing cultures, they need buffered media.
Even in food.
Absolutely. Things like sodium citrate in jams and jellies act as buffers. They help maintain the right acidity for texture, flavor, and preventing spoilage by inhibiting microbial growth.
Okay, so how do they actually do it? What's the mechanism for resisting pH changes?
It's because they have both soldiers ready, so to speak. They have the weak acid component ready to neutralize any added strong base, like OH ions, and they have the conjugate base component ready to neutralize any added strong acid H plus ions.
Ah, so if you add acid, the base part of the buffer reacts. If you add base, the acid part reacts.
Exactly. And because it's a weak acid-base pair, they don't neutralize each other significantly. As long as you don't add too much strong acid or base, overwhelm its capacity, the ratio of the buffer components doesn't change drastically, and so the pH stays relatively stable.
Is there a way to calculate the pH of a buffer, like an equation?
Yes, there is. The Henderson-Hasselbalch equation is the go-to tool. It's pH, psi plus log of the concentration of the base component divided by the concentration of the acid component.
TKA. That's related to the strength of the weak acid, right?
That's right. It's the negative log of the acid dissociation constant, Kessin. The equation beautifully shows that if the concentrations of the acid and base components are equal, the log term becomes 0, and the pH of the buffer simply equals the pKa of the weak acid.
So that's the optimal situation for a buffer, when pH equals pKa.
That's when it has its maximum capacity to resist changes in both directions, acid or base addition. Generally, a buffer works well within about plus or minus 1 pH unit of its pK. That's considered its effective buffer range.
And buffer capacity. That just depends on how much of the acid and base components you have.
Precisely. The more concentrated the components, the more strong acid or base it can neutralize before the pH starts to change significantly. Calculating the pH change after adding strong acid or base involves 2 steps. First, stoichiometry, figure out how much of the buffer component reacts, and then use the Henderson-Hasselbalch or an equilibrium calculation to find the new pH.
Got it. It really highlights the difference. Add acid to water, pH plummets. Add it to a buffer, it barely budges.
Exactly. A huge difference.
Okay, so from buffers resisting change, let's switch gears to a technique designed to measure change very precisely. Acid-base titrations. What are we trying to achieve with a titration?
Titrations are fundamentally about finding an unknown quantity. Usually, it's the concentration of an acid or base solution, but you can also use them to determine things like equilibrium constants.
And how does it work?
You take a known volume of your unknown solution, and you slowly add a solution of precisely known concentration that's the titrant from a burette. You monitor the pH as you add the titrant.
And plotting that pH versus the volume of titrant added gives you that characteristic titration curve.
Yes, and that curve tells you a lot. Let's start with the simplest case, titrating a strong acid with a strong base.
Okay, what does that curve look like?
You start at a very low pH, naturally. As you add the strong base, the pH rises slowly at first. Then, right around the point where you've added exactly enough base to neutralize all the acid that's the equivalence point, the pH shoots up very steeply.
And for strong acid, strong base, where is that equivalence point?
Exactly, at pH 7.00. Because the salt formed, like sodium chloride, doesn't affect the pH. After the equivalence point, you're just adding excess strong base, so the pH continues to rise, but more gradually again.
Okay, pH 7 equivalence, sharp jump. How does it differ if you titrate a weak acid with a strong base?
Ah, now it gets more interesting. First, the initial pH of the weak acid solution will be higher than a strong acid of the same concentration because it only partially ionizes.
That makes sense.
Second, as you add the strong base, you create a buffer region. You have the weak acid and its conjugate base coexisting. So the pH rises more gradually in the initial part of the titration compared to the strong acid case.
Right, because there's a buffer forming.
Exactly. Third, the pH jump around the equivalence point is smaller, less steep. And fourth, crucially, the pH at the equivalence point is not 7, it's above 7.
Why above 7?
Because at the equivalence point, all the weak acid has been converted into its conjugate base. And that conjugate base is, well, a base. It reacts with water slightly to produce hydroxide ions, making the solution basic.
Okay, that's a key difference. Higher starting pH, buffer region, smaller jump, equivalence point above 7. But you mentioned something amazing earlier. You can find the pK from this curve.
Yes. This is one of the most useful things about titrating weak acids or bases. Think about the buffer region. Remember the Henderson-Hasselbalch equation? pH equals pKa plus log base acid. What happens when you're exactly halfway to the equivalence point?
Halfway. meaning you've neutralized exactly half of the initial weak acid.
Right. So at that halfway point, the concentration of the remaining weak acid is equal to the concentration of the conjugate base you've just formed.
Oh, so the base-acid ratio is 1.
Exactly. And the log of 1 is 0. So at the halfway point, the Henderson-Hasselbalch equation simplifies to pH equals pKa.
Wow. So you just find the volume at the equivalence point, go back halfway on the volume axis, and read the pH off the curve at that point, and that pH is the pKa.
That's precisely it. It's a direct experimental way to determine the pK of a weak acid. Very powerful.
That is neat. What about polyprotic acids? Acids with more than one proton to give.
They show multiple steps in their titration curves. You'll see multiple equivalence points, one for each proton neutralized. And similarly, you can find the pKa for each ionization step by looking at the pH at the halfway point between successive equivalence points.
Okay, one last thing on titrations. Indicators. Those chemicals that change color.
Right. Indicators are usually weak organic acids or bases themselves, and their acid and conjugate base forms have different colors. They change color over a specific, relatively narrow pH range.
So you choose an indicator that changes color right around the pH of your expected equivalence point.
Exactly. For strong acid, strong base, the pH jump is so huge, many indicators work fine. But for weak acid or weak base titrations, where the jump is smaller and the equivalence point isn't at 7, you have to be much more careful. You need an indicator whose color change range brackets the specific pH of your equivalence point to get an accurate result. The point where the indicator changes color is called the end point, and you want it to match the equivalence point as closely as possible.
Makes sense. All right, we've talked a lot about acids and bases in solution. Let's shift focus now to solids dissolving, or not dissolving, solubility equilibria.
Yes, moving into heterogeneous equilibria systems involving different phases, like a solid ionic compound in contact with its dissolved ions in water.
What governs this? Is there an equilibrium constant?
There is. It's called the solubility product constant, KSP. For a slightly soluble salt dissolving into its ions, KSP is the product of the concentrations of those ions in a saturated solution, each raised to the power of its stoichiometric coefficient.
And like other equilibrium constants, wait, does the solid concentration appear in the KSP expression?
No, it doesn't. Remember, the concentrations of pure solids or liquids are considered constant, so they're omitted from the equilibrium expression. KSP only involves the aqueous ion concentrations.
Okay, so KSP tells us something about how soluble a substance is. But is KSP the same thing as solubility?
That's a really important distinction. They're related, but not the same. Solubility usually refers to the actual amount of substance that can dissolve in a given amount of solvent to make a saturated solution, often expressed in grams per liter or moles per liter. KSP is the equilibrium constant itself, a fixed value at a given temperature. A smaller KSP means lower solubility, and a larger KSP generally means higher solubility, but the direct calculation depends on the stoichiometry.
Can you give a real-world example where this low solubility is actually useful?
A classic one is barium sulfate, used in medical imaging. You drink a suspension of it, a barium meal, to coat your digestive tract for x-rays.
But aren't barium ions toxic?
Highly toxic. But barium sulfate has an incredibly tiny KST value. It's extremely insoluble in water. So little of it dissolves into toxic Ba2 plus ions that it's safe to ingest for the procedure. Its low solubility is literally what makes it safe.
Fascinating. So KSP gives us a theoretical solubility. Does it always match reality perfectly?
Not always. Simple KSP calculations assume ideal behavior. In reality, especially in solutions that aren't extremely dilute, interactions between ions can affect solubility. Also, if one of the ions involved can participate in acid-base reactions, that can complicate things too. So calculated values are a good starting point, but experimental solubility might differ somewhat.
That brings us neatly to factors that do affect solubility. We already saw the common ion effect suppresses weak acid ionization. Does it affect solubility too?
Absolutely. Adding a common ion decreases the solubility of a sparingly soluble salt. If you try to dissolve, say, calcium fluoride, CF2, in a solution that already contains fluoride ions from NaF, perhaps, less KF2 will dissolve than in pure water. The added F pushes the dissolution equilibrium back towards the solid KF2.
Okay, common ion decreases solubility. What about pH?
pH can have a huge effect if the anion of the salt is the conjugate base of a weak acid. Think about salts containing hydroxide, OH, carbonate, CO3-2, sulfide, S2, or fluoride.
So basic anions.
Right. If you lower the pH, make the solution more acidic, the H plus ions will react with those basic anions, pulling them out of the solution.
Ah, another Le Chatelier effect. Removing a product shifts the equilibrium.
To the right, causing more of the solid salt to dissolve. So, the solubility of salts with basic anions increases significantly in acidic solutions.
This sounds relevant to tooth decay.
Exactly. Tooth enamel is mostly hydroxyapatite, a calcium phosphate salt containing hydroxide ions. Acids produced by bacteria in your mouth react with the hydroxide and phosphate, causing the enamel to dissolve.
And fluoride helps how?
Fluoride ions can replace hydroxide ions in the enamel structure, forming fluorapatite. Fluoride F is a much weaker base than hydroxide, so fluorapatite is far more resistant to dissolving in acid. That's the basis of fluoridation.
And this pH effect on solubility has bigger environmental implications too, right? Like ocean acidification.
Yes, this is a major concern. As we put more CO2 into the atmosphere, more dissolves in the oceans, forming carbonic acid and lowering the ocean's pH.
Making it more acidic?
Right. This lower pH reduces the concentration of carbonate ions, CO32. And many marine organisms, like corals and shellfish, need carbonate ions to build their shells and skeletons made of calcium carbonate.
So less carbonate available means it's harder for them to build or maintain their structures.
Exactly. It stresses these organisms and can impact entire marine ecosystems. It's a direct consequence of changing the solubility equilibrium of calcium carbonate in the oceans.
Wow. Okay, besides common ions and pH, what else affects solubility? Complex ions.
Complex ion formation can dramatically increase solubility. Metal ions, especially transition metals, can act as Lewis acids and react with Lewis bases molecules or ions like ammonia, NH3, cyanide, CN, or hydroxide, OH, to form soluble complex ions.
What does that increase solubility?
Let's take silver chloride, AgCl, which is very insoluble in water. If you add ammonia, the silver ions, Ag+, react strongly with ammonia molecules to form the soluble complex ion AgNH3 2 plussed up. This reaction effectively removes free Ag+ ions from the solution,
Pulling them out of the AgCl dissolution equilibrium.
which, again, by Le Chatelier's principle, shifts that equilibrium to the right, causing more solid AgCl to dissolve. So, insoluble AgCl dissolves readily in ammonia solution due to complex ion formation.
So complex ions generally make things more soluble. What about amphoterism? That sounds complicated.
Amphoteric substances are kind of special. They are oxides or hydroxides, often of metals like aluminum, zinc, or chromium, that are insoluble in neutral water but can dissolve in both strong acids and strong bases.
Both. How does that work?
Well, they react with strong acids, as you'd expect a base to react, but they also react with excess strong base, typically forming soluble complex hydroxy anions. For example, aluminum hydroxide, AlOH3, is insoluble. Add acid, it dissolves to form Al3 plus Sef. Add strong base, it dissolves to form the complex ion AlOH4.
Is this used anywhere practically?
Yes, the purification of aluminum from its ore, bauxite, relies on this. Bauxite is mostly aluminum oxide, Al2O3, mixed with impurities like iron 3 oxide, Fe2O3. Aluminum oxide is amphoteric, but iron 3 oxide isn't.
So you can use a strong base.
Exactly. Treat the mixture with hot, concentrated sodium hydroxide solution. The amphoteric aluminum oxide dissolves, forming AlO4, but the basic iron oxide impurity does not. You filter off the solid iron oxide, and then you can recover pure aluminum hydroxide from the solution.
That's clever. Now, bringing several of these factors together, you mentioned the Flint water crisis earlier. How did these solubility principles play into that tragedy?
Flint is, unfortunately, a perfect storm illustrating these concepts. The key issues were changes in the water source and, crucially, the water treatment.
What went wrong with the treatment?
Well, the previous water source from Detroit had corrosion inhibitors added, specifically phosphates. These phosphates helped form a stable, insoluble layer of lead phosphate salts on the inside of the lead pipes, protecting them.
Okay, protective layer.
When Flint switched to using water from the Flint River, they didn't implement effective corrosion control, so no phosphates were added. That protective layer started to dissolve.
Just removing the inhibitor was enough.
That was part one. Part two was the water chemistry itself. The Flint River water was more corrosive. It had a lower pH and higher chloride levels compared to the Detroit water.
Okay, how did lower pH affect the lead pipes?
Remember, solubility increases in acid if the anion is basic. The lead compounds forming scale often involve basic anions like carbonate or hydroxide. Lowering the pH made these protective compounds more soluble, accelerating corrosion.
And the higher chloride. Didn't we say common ions usually decrease solubility?
Usually, yes. But chloride is also a Lewis base that can form complex ions with lead. While lead 2 chloride itself isn't very soluble, at high enough chloride concentrations, soluble complex ions like PbCl3 or PbCl42 can form.
Ah, so the high chloride actually increased lead solubility by forming these complexes.
That's believed to be a major contributing factor. So you had the lack of inhibitor, the lower pH dissolving the existing scale, and the high chloride potentially forming soluble complexes all working together to leach dangerous amounts of lead into the drinking water.
It's a devastating example of how interconnected these chemical factors are and the vital importance of understanding them for public health.
Absolutely. A tragic illustration of aqueous equilibria with profound consequences.
Okay, let's wrap up with how we can predict and control precipitation. How do we know if mixing two solutions will form a solid precipitate?
We compare the reaction quotient, Q, with the solubility product constant, KSPQ. It's calculated the same way as KSP, but using the initial ion concentrations before any precipitation occurs.
So how does Q tell us what will happen?
There are three possibilities. If Q is less than KSP, the solution is unsaturated, and no precipitate will form. More solid could still dissolve. If Q equals KSP, the solution is exactly saturated, it's at equilibrium. If Q is greater than KSP, the ion concentrations are too high, the solution is supersaturated, and a precipitate will form, reducing the ion concentrations until Q equals KSP again.
QKSP means precipitation. Can we use this predictively to separate ions?
Yes, that's called selective precipitation. If you have a mixture of ions whose salts have significantly different KSP values with a particular counterion, you can add that counterion carefully.
How does carefully work here?
You add just enough of the precipitating reagent to exceed the KSP of the least soluble salt, causing it to precipitate out, but not enough to exceed the KSP of the more soluble salt, leaving that ion still in solution. For instance, AgCl is much less soluble than PbCl2. You could add chloride ions slowly to precipitate almost all the Ag+ before any significant amount of PbCl2 starts to form.
So you filter off the AgCl, then maybe add more chloride to get the lead out.
Or use a different reagent for the lead later. This idea is the foundation of traditional qualitative analysis schemes.
Qualitative analysis, what's that?
It's a systematic procedure, often used in introductory chemistry labs, to determine which specific metal ions are present in an unknown mixture. You don't find out how much, just if they're there, hence qualitative.
How does it use precipitation?
It uses selective precipitation in stages. Cations are typically divided into about 5 groups based on the solubility of their chlorides, sulfides at different pHs, hydroxides, and carbonates. You add a specific reagent to precipitate one group, filter them off, then treat the remaining solution with the next reagent to precipitate the next group, and so on.
So it relies heavily on those differences in KSP values and controlling conjunctions like pH.
Absolutely. For example, some metal sulfides will precipitate in highly acidic solution, low sulfide ion concentration, while others only precipitate in neutral or basic solution, higher sulfide ion concentration. Controlling the pH is key to separating those groups using hydrogen sulfide.
What a fascinating journey through this hidden world within water. We've gone from the subtle common ion effect to the vital role of buffers keeping us alive, the power of titrations to reveal unknowns, the delicate dance of solubility, and how factors like pH and complex ions can change everything, even leading to crises like Flint if misunderstood.
It really underscores how these aren't just abstract concepts in a textbook. They are active principles governing biological systems, environmental processes, industrial chemistry, and yes, even the safety of our tap water. They're truly central to chemistry.
So the next time you look at a glass of water, or think about the ocean, or even just your own body chemistry, maybe pause for a second. Remember that constant, intricate balancing act of aqueous equilibria happening everywhere, all the time. It's the unseen chemistry shaping so much of our world.
Keep looking closer at the chemistry around you. Thanks for diving deep with us today.
And thank you for tuning in. Until next time, stay curious.